Hello and welcome. Today we are going to crack one of the most fundamental source codes of the entire universe. You know, that invisible force that governs, well, everything. From a simple apple falling from a tree to the grand cosmic dance of the planets. We are, of course, talking about Newton's universal law of gravitation.
I mean, think about it. What is that invisible tether that keeps the moon circling us? And what keeps our feet planted firmly on the ground? This is the exact kind of mystery that fascinated thinkers for centuries, and it's the puzzle that Isaac Newton was determined to solve.
Now, Newton didn't just have some eureka moment and find the answer out of thin air. No, he built it piece by piece like a cosmic detective on the case of a lifetime. And he did it by following two absolutely fundamental clues he observed about how our universe works.
So, we're going to follow right in his footsteps and build this famous law together, step by step. First, we'll look at the role mass plays. Then, we'll get into the super important effect of distance. After we combine those two clues, we'll uncover that final missing piece that makes the whole cosmic puzzle just click.
Okay, clue number one is all about mass. It kind of makes sense, right? The more stuff something is made of, the stronger its gravitational pull. But here's Newton's genius insight. The force isn't just about one object. It's proportional to the product of both of their masses multiplied together. That's why the pull between the Earth and the Sun is so unbelievably huge. It's their combined colossal masses working together.
The second clue, which is all about distance, is a little more surprising. It follows what we call an inverse square law. And what that means is, as two objects get farther apart, the gravitational force between them gets weaker, and it gets weaker fast. So if you double the distance, the force isn't just cut in half. No way. It becomes 4 times weaker. If you triple the distance, it's 9 times weaker. This rapid drop-off is absolutely crucial.
So when we put those two cosmic clues together, we get this really clear relationship. The force of gravity is proportional to the product of the masses divided by the square of the distance. You can see it right there. This is basically the skeleton of the law. We are so close to the final equation now.
Okay, let's take that relationship and turn it into the final code. You see, that little proportional to symbol is a great start, but to make it a tool we can actually use for real-world calculations, we need to turn it into a precise, workable equation.
And there it is. By swapping out that proportionality symbol for a good old equals sign and adding one new element, that capital G, we now have the complete universal law of gravitation. This right here, this is the formula that describes that invisible tether holding the entire cosmos together.
So let's quickly unpack what each part of this means. First up, F is the gravitational force itself. We measure it in a unit called newtons, which is, a pretty fitting tribute to the man himself. Then you've got M1 and M2. These are just the masses of our two objects, and in the world of physics, we measure those in kilograms.
And D is the distance between them, measured in meters. But here's a really important detail. You don't measure it from their surfaces. You have to measure it from their centers of mass, basically the average position of all the stuff that makes them up.
All right, let's zoom in on that final, kind of mysterious piece of the puzzle, that capital G. This isn't just some random letter. It's a fundamental property of our universe, something we call the universal gravitational constant. Think of it as the magic number, the conversion factor that makes the whole equation balance out perfectly.
And this is its value. It was painstakingly measured by a scientist named Henry Cavendish way after Newton's time. And just look at how incredibly small that number is. That's a decimal point, followed by 10 zeros before you even get to the 6. It's almost impossible to imagine how tiny that is.
And this constant G has its own unique and, pretty complex-looking SI unit, Newton meter squared per kilogram squared. Now that might seem like a total mess, but it's actually genius. It's perfectly designed to cancel out all the other units in the equation, so what you're left with at the end is just newtons. It's incredibly elegant. So here's the big takeaway. The reason gravity seems so weak in our everyday lives, it's all because of how tiny G is. That's why you don't feel a gravitational pull towards your chair or your coffee mug. For the force to be strong enough for us to notice, at least one of the masses involved has to be absolutely gigantic, like, say, a planet. Okay, so we've got the equation, we understand all the parts, but why does it matter? Why is this one single line of math so important? Let's dive into just how profound its implications really are. Let's start with a little thought experiment. We all know the Earth pulls a stone down, which makes it fall.
But remember Newton's third law of motion? For every action, there's an equal and opposite reaction. So, does that mean the tiny little stone is also pulling the entire planet Earth up towards it?
And the answer is a definite yes. And this is just a brilliant illustration of how the law works. The force of attraction is perfectly equal in both directions. But because force equals mass times acceleration, that exact same force causes a really noticeable acceleration in the small stone, about 9.8 meters per second squared. Meanwhile, on the unimaginably massive Earth, that same force produces an acceleration so ridiculously infinitesimally small that it's completely impossible to detect. And this right here is what makes Newton's law truly universal. The exact same rule that makes an apple fall to the ground is the very same rule that holds entire galaxies together across billions of light years. The physics happening in your backyard is the same physics happening in the deepest corners of space.
I mean, just think about the sheer power of this single equation. Before Newton came along, all the things on this list were seen as totally separate mysteries. But his law connected everything. It explained why we're stuck to the ground, why the moon orbits us, why the planets go around the sun, and even how the pull of the moon and sun creates our ocean tides. We've even used it to discover new planets just by noticing their gravitational tug on other ones.
It really all boils down to this one simple, powerful idea. Everything with mass is connected to everything else with mass. You are gravitationally attracting me, the moon, and the most distant star in the universe, and all of them are attracting you right back.
And maybe that's the ultimate beauty of what Newton discovered. He showed us that behind all the chaos and complexity of the universe, there's a simple, elegant, and understandable order. It really makes you wonder, doesn't it? What other profound cosmic codes are just out there, waiting for us to crack them?